So hi everyone, welcome to the lecture 3 of Hardware Software Codesign for Edge AI. And in this lecture we'll be discussing about the efficiency metrics for embedded machine learning. So I hope you watched the lecture too, because we discussed about the basic components and what makes a linearly connected neural network, what makes a convolutional neural network. We discussed about grouped convolutional layers, stepwise convolution, and today we'll be just discussing about how to calculate the efficiency of models which are constructed using these basic machine learning. Okay, so we have three directions to calculating the efficiency. Definitely, we want a smaller size when we're talking about embedded machine learning. In fact, even for cloud-based machine learning, we still want smaller size because it is just more efficient, right? So this is one dimension. Then how fast the machine learning can perform, how quickly can it get us the output, that is what we want to improve, so faster. And then we want it to consume as less power as possible, therefore we want it to be greener and energy wise efficient. So how to calculate the size of this, how small of the machine learning model is. So we do that by measuring the storage capacity of that model. How fast the model is, we calculate that by latency, and how much power the machine learning model is going to consume per calculation of the inference, let's say, that we do it by energy calculation. So we'll see all the three metrics, how do we quantify storage, the latency, and how do we quantify energy. Ultimately, it boils down to actually the computation and the memory requirement. So we're having certain parameters with us. So the memory related parameters include the number of parameters themselves in the machine learning model which are to be trained, the model size, and the total / peak number of activations. And then from the computational related aspect side, so these are all the memory related issues. From the computational related side, we calculate what are the total number of multiply and accumulations which are to be performed inside the machine learning model, the complete pass. Then what are the floating point operations and the floating point operations per second, and to generalize that, total number of operations and operations per second. So let's look at latency. So on left side you can see that the latency is very high. It's taking about 638 milliseconds for doing segmentation on one frame. On the right side you see that there is an efficient vision transformer which is just taking 46 milliseconds to do the frame. And this metric is intersection over union. This is not related to our machine learning thing. I'll discuss it later. That it's basically describing how good the model is in itself. So both the models perform good, but one is having high latency and another one is having low latency. So latency shows that how much time it takes to output for the complete machine learning model to output one what do you say output, right? So that's what latency is. Throughput measures the rate at which the data is processed. So again, you can see that on the left we have a low throughput video in which there are 6.1 videos per second being processed, and on the right there's 77.4 videos per second being processed. So it's a high throughput thing. So this high throughput, so now generally the convention is that higher throughput translates to lower latency, that pipeline, the more the number of things which I'm getting into the pipeline, the higher the throughput would be, as opposed to lower latency translate to higher throughput. So let's discuss two scenarios. So it entirely depends on the design choice, right? On one side you see that there is a design in which a single processing of image takes 50 milliseconds. So the latency is 50 milliseconds as evident from the image. And throughput would be in in 1 second, how many images would pass? 20 images would pass if we use this design technique. So throughput is 20 images per second, as opposed to a parallelized architecture in which 4 images are being processed parallelly, and each image is taking 100 milliseconds. So the latency is 100 milliseconds, but you see that in 1 second, how many images will pass through in total? 40 images. So the throughput is higher. So it does not necessarily mean that higher throughput means that I'm having lower latency. No, it entirely depends on the design choice. And this is where FPGA would actually help us. FPGAs, which we later on study, I think around lecture 7 or 8, we'll have a good introduction of FPGAs, GPUs, right? So FPGAs help us in parallelize the task. So latency is generally composed of two parts. So you see that when we're actually, so this is the total, like, one pass. So it includes two components. One is the memory related thing, and the next thing is the computational related thing. So we load the input and we load the weight. So this is we're talking about, let's say, layer 1 of the architecture, and this is the layer 2. AlexNet, we saw that we have 5 layers. So this is not image by image, this is layer by layer. So we load the input to the first layer and we load the weights of the first layer, and then we do the computation of the first layer and store the output. In parallel, as we are loading the weights, as we are doing the computation of the layer 1, we can load the inputs of the layer 2 and load the weight, and once the output is ready, then we can actually start doing the computation of this part. So data movement and computation can be overlapped. This is something which we need to understand, and therefore the latency is a max of what is taking more time. If loading is taking more time, then like the memory operations, then we will take this as the latency, and if the computation is taking more time, then we will take the computation as the latency, right? And this is talking about a particular scenario when the data movement and computation are being overlapped. So it entirely depends on your design structure, but this is the general case which we follow, right? So for doing the computations, the time taken for the computation, it is the number of operations which are present in the total neural network, like in the complete neural network, upon number of operations that processor can process per second. So this information comes from the hardware specification, and the top thing, the number of total operations in the neural network, comes from the neural network specification. So always you'll have a hardware specification and a neural specification in order to figure out your computational time. Same is the case with data movement of weights and data movement of activations. So when we're calculating the memory, what is the total time taken for the loading of the input and loading of the weight. So it includes of two parts. One is the input and the weight. So activations is nothing referring to here but the input, and the total the T data movement of weights is the neural network model size. What is the model size? Let's say for AlexNet it's around 224 MB, let's say. And what is the memory bandwidth of the processor? That how much memory can the processor put in one go? So simply put, memory bandwidth is the maximum amount of data that can be transferred between the memory and the processor at a single unit of time. So usually it's calculated in seconds, so it's gigabytes per second, a popular metric which you might have heard. There are different types of memories actually, since we are discussing about this, so let's just discuss a little further. That there are different types of memories: DDR4 memory, DDR5 memory, LPDDR4 memory, and all are having different bandwidth capabilities. So it's entirely dependent on the hardware specification, that how much bandwidth your memory can support. And also it's dependent on the clock speed as well, like usually at higher clock speeds contribute to an increased bandwidth of memory. So theoretically you can calculate the memory bandwidth of a processor. As of now we are not discussing, but I can just simply write the formula that, just a second, I can simply write the formula as let me take out the pen. It can be written as memory bandwidth is equal to data bus width multiplied by the memory clock speed into the total number of channels which you're having. So just total number of channels. So we will actually discuss this somewhat later, maybe not, but as of now you can just see that how the data movement of weights is calculated. It's both the weights and activations, the denominator is same, memory bandwidth of processor. But for weights, it's the neural network model size in the numerator, and for data movement of activation, it's the input activation size plus the output activation size. These things will become little more clear when we discuss it with an example, so wait for it. So you see that the energy consumption uh, is actually like, the more the data movement, the more memory references and more energy has to be spent. So energy as a metric is calculated in picojoules, and if it's a 32-bit int add operation, then it's taking on 0.1 picojoules of energy. And you see that it's logarithmic scale. So on the higher spectrum, we have a memory movement of from 32-bit DRAM memory, reading 32 bits of data from DRAM memory, and each time you read, you have to spend 640 picojoules. So the more your references are being made to the memory, the higher the energy consumption of the memory model is. So you try to ensure that even though no matter how big or small the memory size is, if something has come into the GPU memory, it stays there. Like if something has come from the DRAM memory, until all the operation is done on it, it remains there. You can see that on the same metric we have SRAM cache, how much energy is spent using to do an SRAM cache read, then doing a 32-bit int multiplication or 32-bit float multiplication. So it also depends. We try to do int multiplication because it saves energy as well as it will save a lot of bits as well. Okay, so number of bits is same, so it's just energy efficient here. And reading 32-bit from a register file. So these are like some energy metrics which we try to observe. So besides that, most important thing, as I discussed, we want to actually study about the number of parameters, the model size. So memory related ultimately boils down to computation memory related metrics. So firstly we'll discuss the memory related metrics, that and first thing which we'll be doing in that is number of parameters which are there in the model. So number of parameters is the parameter count of the given neural network. That is the number of elements in the weight tensor. So weight is what we're actually training. So if we are given this machine learning model, let's say, then what we're actually training inside it are these synapses, the connections which you are seeing. And how many connections are there? If there are 5 nodes in the input and 3 in the output, then how many such connections are there? Answer is simple, 5 into 3, right? 15. And a very simple way to think of it is that, let's say this batch size is 1 right now, right? So independent of batch size, whatever the batch size is, the number of parameters which we have to train would remain the same, C naught into Ci. So if you increase the number of parameters here, the batch size here, then also the number of parameters will remain same. So because later on when you see that when we calculate activations, peak activations, and when we try to calculate max, you will keep on seeing similar things repeating, but all of them mean different actually, and you'll have to be well aware of what we are discussing right now. So it's number of parameters. So it's C naught into Ci. It's very straightforward here. Next we have convolution layer. So in convolution, the number of parameters if you have to calculate, so what is actually getting trained are these small blocks which you see here in our filters, what we call as filters or kernels, right? So in each filter or each kernel, how many parameters are there to be trained? So it's kh into kw into ci, right? And how many total number of filters are there? C naught. So therefore total number of parameters to be trained inside a convolution neural network in a particular layer where the number of kernels are given and the size of the kernel is given is C naught into Ci into kh into kw. Then as we had discussed previously that in group convolution what we do is that there is a reduction by a factor of g. So both the C naught, since there are two groups which are formed, right? So effectively the number of connections which are to be formed, they are reduced by both in C naught and Ci by a factor of G. So C naught by G, Ci by G. But in total, there are G groups which are being formed, so a single into G operation is there. Ultimately, when we multiply together, 1G gets cancelled with 1G, and finally we have a reduction by a factor of G. So the number of parameters go down from convolution to group convolution by a factor of G. And then finally we have a depthwise convolution, which is the extreme scenario of the group convolution, in which the G becomes equal to Ci. The number of groups which you are making inside this is equal to the Ci, and therefore each channel has its own convolution. So previously this length was equal to the dimension of the filter which we had drawn, but now all of them are being independently handled. So this Ci becomes equal to G, and therefore there is a further reduction in the number of parameters which are there. So now let's take this example which we had discussed from lecture 1 itself, AlexNet. In lecture 1 we tried to get an intuitive understanding. In lecture 2 we saw about how to calculate the number of channels and height and width after each layer. Now is the time to calculate the number of parameters. So let's do it for I've placed the number of parameters count here, and we have convolution, like this is a convolution operation which is here. There are group convolutions also available, right? And in MobileNet we saw there is a depthwise convolution. So we can calculate the number of parameters. It's simple and straightforward. That total there are 96 kernels, 96 filters which are there. So therefore this first factor is 96, which is your total number of filters which are available, right? And then kh into kw. So this is 11 cross 11 which is given to you, and each is having a depth which is equal to the channel of the previous the channel dimension of the previous layer. So this 3 is coming from here. So this becomes total equal to 24,848. Similarly, if you look at this particular layer, how many in pooling layer we discussed that there are no parameters to be trained. So here the number of parameters are basically 0 in the pooling layer. Next we see for a 5 cross 5 convolution having 256 kernels. So 256 comes directly from the number of kernels which you have available, and 5 cross 5 comes from kh into kw. And how many channels were there in the previous layer? That comes to this point Ci here. And since there are 2 groups, so therefore divide by 2, the number of total parameters which are to be trained here is 307,200. Similarly, you can calculate all these other parameters, and in total what we figure out after we do the addition operation is we have 61 million in total. One thing interesting to note is that as we come to the last part of this last fully connected layer, so we do a C0 into Ci, right? And this, if you look at this particular, so it's 4096 into 4096, and this is a very huge number. In fact, even this is a very huge number. These are your total number of output nodes, and these are the total number of your input nodes, right? So input into output, as we discussed, because we are converting from a matrix to a fully connected node, like a linear layer, right? So this number is huge, this number is huge. So unnecessarily lot of connections are there in linearly connected layers. Lot of parameters are there, sorry. And if we add all of them, then total 61 million. Next we look at model size. So once we've calculated the total number of parameters, so model size measures the storage for the weights of the given neural network. Essentially, when we're talking about the model size, we're referring to the number of parameters and how much width or how much space each parameter is taking, which is determined by its bit width. So some common units of the model are in megabytes, kilobytes, or in bits maybe. And if the whole neural network is using the same data type, then this formula can be used, or else we need to break it down, like, you know, this part is using floating point and this part is using int operations. So that's how you can also calculate model size. Now let's take an example of AlexNet, with, and in the last slide we had looked at it has 61 million parameters. So if all weights are stored as a 32-bit number, then the total storage would be 61 into 4 bytes. 32 bits is 4 bytes, so it's 224 MB. But if we quantization is something which we'll do in the next lecture. So if we quantize all these 32-bit operations into 8-bit operations, let's say 8-bit integer operations, then the total storage will be about 61 million into 1 byte, which is 61 MB. So you've saved on a lot of model size. You might be wondering that, okay, what about all the other connections which are there, like the input and output layer? So they do not consume memory. Those are just the definitions of the architecture. Like each of the pixels you don't have to define. They are made with so each output layer is actually made by what? The input which is coming multiplied by the weights that is giving you the output. So they don't have to be stored anywhere. So model size in the architecture, the definition of the architecture, that how the machine learning model is architectured, right? That takes some space, but that is like, constant space. And that is very small. Defining the architecture is nothing. But filling up the pixels inside each of those things is what is computationally heavy. So let's go further and discuss about the number of activations. So I told you that previously also activations, what are activations? So in neural network, the total number of activations refers to the total number of output values generated by the neurons in the network. Basically in a single forward pass, you will have during a forward pass, at each layer there will be an output generated by the previous layer after being multiplied by the weight. So that is referred to as the number of activations. So activation is the memory bottleneck in inferencing in IoT, and it's not the number of parameters which are causing the issue. And you can see that the parameters in this, let me take out the pen. So the number of parameters between these two models, MobileNet and ResNet, although they have decreased 4.6 times, but the peak activation in the MobileNet has increased by 1.8 times, and this is not conducive for IoT. So this has become a bottleneck. And sometimes what happens is that the last layers, let's say the memory usage. So this is per layer memory usage, and in certain layers, previous layers, so if the constraint of the microcontroller is 256 kb, the last things will actually fit in. If you're calculating the total number of parameters and everything, so you might calculate, okay, it will all fit in. But if a certain layer is actually getting like, lot of activations are coming in that, it has to store that in a flash memory, but it cannot because it's just constrained by 256 kb of flash memory. So it cannot be trained on it. The whole thing will break down, like the computation will not be possible only until unless you do some efficient, you break that down, that particular layer. But breaking that a single layer into computations of different layers is another complexity in itself. So point being that we cannot just just depend on number of parameters. We need to look at the number of activations, which is layer dependent. So activation is the memory bottleneck in training and not number of parameters. This we have looked at, and even though the number of parameters are decreasing, but the activation size is increasing. So let's calculate the total number of activations in AlexNet, and as I told that it is simply the number of outputs which it is producing, right? So if the input image is of size 3 cross 224 cross 224, then the total number of outputs, like the total number of pixels which are available here, the values which need to be calculated is 150 in this layer. And if you apply this channel, like this 96 kernels of each of 11 cross 11 size, then the total number of outputs in this particular layer, in the output of this layer right here, would be 290, 400. 2,90,400. So similarly, you can calculate that after each layer, what are the total number of values which are going into as an input to the next layer, and what is the output which is supposed to come from that layer. So this way, if you add all of this together, you will get the total number of activations. But then if we want to calculate the peak activation, it is that for a particular layer here, because for a particular layer you have to get both the input also stored and the output as well stored. Like this input also has to be stored, and this output where you're processing, that also has to be stored somewhere, right? You just at a single point of time. So the number of input activation and the number of output activation, whatever is maximum in as a combination of these two things, that you pick up, and we can easily see that in the first layer itself the peak activation is coming around the total number being 440,928, 4,40,000 somewhere around that. Then comes a more prominent metric, which is multiply MAC operations, multiply and accumulate operations. So a single operation of B into C and then total added with A and stored in back in A is known as a MAC operation. So if there is a matrix, let's say of M cross N, matrix of size M cross N being multiplied by a vector of size N cross 1, right? So the total number of, so you can see that these four things when multiplied by these four would lead to one pixel here. So in the first thing itself, how many max are being consumed? Total number of N max are being consumed, because each of these would lead to a single MAC operation. This multiplied and added, this multiplied and added, this multiplied and added, this multiplied and added, and together it will fill up this pixel. So total number for multiplying each of these rows with the column in this would lead to N max, and how many such rows are available together? M. So total number of max is M into N. And similarly, if you increase the batch size, or let's say that a generic multiplication, matrix multiplication where we are increasing N, so it would be total M into K into N, right? This you can also easily calculate. So now let's look at max of different linear layer, convolution layer, group convolution, depth convolution. So if the batch size is assumed to be 1, then what is it? Simply Ci being multiplied once with this, and other time with this to produce the output, this and this output, right? Which you're seeing here on the screen. So it's simple, straightforward. C0 into Ci is the total number of max. Total number of max for a linear layer. Do not confuse this with the metrics which we had seen previously, the number of parameters. The number of parameters was also same, but that was entirely different calculation than the max which we are calculating here. Alright. Then for the convolution, so if this is the convolution, then for filling up each pixel in the output layer, how many calculations we have to do? KH into KW into CI. So if you do KH into KW into CI, number of operations, basically each of these getting multiplied and added, then you get one pixel here. Okay, so this is for one pixel, and total how many number of pixels are there? C0 into H0 into W0. So therefore together multiplied in a convolution will give you the number of max in a convolution layer. For group convolution, we had figured out that it's just a reduction by a factor of G. So Ci by G, C0 by G, and total number of groups which are formed is into G. Therefore 1G gets cancelled 1G. Ultimately it's just a factor of G which remains. And at depth wise, G becomes equal to C. Therefore these are the number of max. So as you see that we come from convolution to group convolution to depth wise convolution, the number of max decrease. Again, let's try to calculate the number of max which for an AlexNet. Previously we saw activations, right? This time we'll calculate max. So for max, what is required if you're in this convolution? So here I've placed this block here. So you can easily calculate that your kernel height and kernel width is 11 cross 11, and your output height and output width, that is coming from here, right? And the input channel is coming from the how many channels which you have here in the, basically your channel dimension. Actually your channel dimension is determining that. Again, for the group convolution you can do it this way. So the total number of max you can calculate for AlexNet. So now we want to discuss the efficiency metrics related to computation. So max we have already discussed, right? Now is the time to discuss floating point operations. So a single multiply is what? A floating point operation. A single add is what? A floating point operation. So one multiply and accumulate operation is nothing but two floating point operations. So in AlexNet we had calculated like if you add all of these together, it would be somewhere around 7. Oops, sorry. It would be around 724 million max, right? And each of which each MAC has two floating point operations. So therefore, how many total number of operations? 1.4 giga. 1.4 giga floating point operations in order to calculate the total AlexNet. This is what you have to spend. Then we can calculate per second that the floating point operations per second which can be performed by the processor, maybe it is your GPU or your FPGA, that is known as flops, floating point operations per second which can be performed. So given the flops of a particular embedded device and given the machine learning model's MAC, you can calculate that how much time it's going to take. As we see, like when we discuss about NVIDIA's GPUs, in fact I'll open their web page and show it to you. So this is the homepage of NVIDIA's NVIDIA Jetson, and you can just explore explore what's in embedded computing. So feel free to go over through that. I'll just quickly read. AI is revolutionizing businesses with automation, improved data analytics, and enhanced engagement. NVIDIA Jetson is the leading platform for robotics and embedded edge AI applications, which we are discussing in the course. So we'll be taking a look at NVIDIA Jetson, and is supported by NVIDIA Jetpack SDK for accelerated software development, and it provides pre-built cloud-native software services to fast-track development and deployment of sophisticated edge AI applications like Gen AI, computer vision, and advanced robotics. And Orin series gives you unparalleled AI computation, large unified memory, and comprehensive software stack. All these they are defining, it's good to read. I had shown you this architecture as well. When we discuss more, you will further realize that on the lowest level we have the NVIDIA Jetson, and then on top of it we have a Linux operating system running, so which takes care of all your operating system related tasks, and then you have security as well inbuilt into the secure boot and everything. So edge AI security is also ensured. On top of that, you have an AI stack in which you can using which you can interact with the hardware, and CUDA, CUDNN libraries, CUDLA libraries, TensorRT, and then we have AI frameworks and AI workflows which are there, and then ecosystem of different apps and services. For each of these Jetson series, what is actually defining them is the number of operations which they can do. So here they have not mentioned flops but tops. As we'll discuss in the next slide, that what is operations per second, or right, and tera operations per second. So how many tera operations per second it can perform? 275. So the higher the number, the quicker the AI model will run on it. But at what cost? At the cost of energy also. So it's consuming more energy, you can see here. So we have Jetson AGX Orin series, Jetson Orin NX series, Jetson Orin Nano series. We have Xavier series as well, like there are different variants in that, and Jetson TX2 series, and Jetson Nano having just 0.5 T flops, tera floating point operations capabilities. So as I told that we'll be discussing about number of operations. So it's not necessary that all the operations are floating point, are not always floating point. That's not necessary condition. To generalize the number of operations is used to measure the computational amount. So in the Nano series, floating points, any processor can handle a particular data type. So floating point is something which most of these embedded things should cater, they definitely have to. But a more efficient would be calculating the integer operations, like doing it in integer, or there are different data types which we'll discuss in the next lecture, like mixed floating points or BF series or BF data types. So we'll discuss in the next lecture, so hold on for that. And based on that, you can again calculate the total number of operations which are going to happen. So it's very similar to flops. So this is it for lecture 3. In lecture 4, we'll begin with actually discussion on quantization, which is converting a higher data type to a lower data type, and what are the ways and techniques to do that. And we'll actually start getting an entrance. Quantization is something which is very necessary whenever we come to FPGAs or GPUs, because you cannot run floating point things in its full magnitude. So you try to reduce that, and quantization is a standard technique which we have to use in order to bring down the number of bits from 32 floating point bits to, let's say, 8 bits of integer, right? So we'll discuss that in the next lecture. Thank you so much.